Yes, so thank you for having me back. I spoke with the collaboration, Elizabeth, as you mentioned, about a year and a half ago. The same topic, fitting the exotic hadron spectrum with an additional quark. I got a lot of great feedback from that talk that I gave then, and refined the theory quite a bit, and I'll mention how I did that. And this talk shows some aspects of the refined theory, the refined mappings, and also some new predictions for LHCb. So the theory that I have has a seventh flavor of quark. Its charge is minus one third, and its mass is around 2.9 GeV, so in between that of the charm and the bottom quark. And because I have a number of equations in this talk, I'm giving it the symbol of F to be able to talk about it. So if that quark is assumed to exist, then I'm claiming that most of the observed exotic hadrons can be neatly mapped as just mesons and baryons in the quark model, ones that involve that quark. So for the theory to be valid, there's a number of things that have to be shown, and I will not be talking about them in this talk, but some of them are listed there below, and there's a link also below where I talk about some of them and reference another paper that talks about more. The big difference from when I talked with the collaboration a year and a half ago is that my underlying theory has some additional scalars, and I had not thought that those were important for the discussion of the seventh quark. But then I realized that one of them may be important. And so the additional part here is that there is a light scalar that has no interaction with any gauge bosons, but it does interact with some quarks. And so its main interaction terms are with CC bar, and then it also interacts with this additional quark together with the S quark or the D quark. And the connection with the D quark is Cabibbo suppressed relative to that with the S quark. So given that interaction, then the theory can reproduce the observed production and decay modes for what I'm calling F quark hadrons. Anytime that a CC bar is created, whether it's created from E plus E minus or from a B meson decay, for example, that CC bar can transform to the scalar through the interaction and then to FS bar or FD bar. And so that's how F quark hadrons are produced in this model. The way they decay is very straightforward. The F decays by the scalar to an S and a CC bar or to a D and a CC bar. The model also has a connection between the F and the C quark connected by the W boson. And so a weak decay like this is also possible in the model. So that's how the production and decay of these happen, and these modes could explain all of the observed production and decay of the exotic hadrons that I'll be talking about. I want to give a quick example first, which is the charged pentaquarks that have been observed by LHCb. So in this model, they're sigma F baryons that have isospin 1. So they have an F quark and two up quarks. So they've been observed by LHCb being produced from the decay of a lambda B going to a pentaquark and K minus, and then decay to a proton J psi. So in this model, the production starts with a normal weak decay that generates CC bar. The scalar then turns that CC bar into a D bar F, and then a gluon turns DD bar into UU bar. And so that's how the sigma F meson of this model is generated. Then the decay is very simple. The scalar, the F turns into a D with a CC bar. So I'm claiming that in this model, those charged pentaquarks are sigma F baryons, and there is some mass spacing pattern observed for the narrow ones here. I didn't put the 4380 in here, but for the narrow ones, there's an observed pattern. And so if I want to compare those to the narrow baryons in the sigma spectrum, is there any part of that spectrum that has a similar mass spacing? And the answer is yes. This part of the sigma baryon spectrum has a very similar set of mass spacings, similar to within 1%, except that what I'm calling the sigma F baryons are a little under 2700 MeV heavier. And that would imply that the mass of the F quark is 2.8 to 2.9 GeV. So then in this model, the 4459 is just the isospin partner of the 4457. And then the 4338 is an isospin zero lambda F baryon, which is analogous to the lambda 1670. So I'm saying that all of these lambda F and sigma F baryons are in the same quark model states as the analogous sigma and lambda baryons that I've mentioned there. But there's a lot lower mass lambda and sigma baryons as well. There's all of these, and going down to the lowest mass ones. And so, if for the analogy to work, then it means that there should also be lower mass sigma F and lambda F baryons. So I'm predicting that these additional baryons exist, these lambda F and sigma F baryons. And what I've shown here is the observed 4338 that I'm calling a lambda F baryon. And its observed production is from a B meson decay. So some of the other lambda F baryons should also be produced in a B meson decay just like that. But some of them will not have enough mass to have the decay going to a J psi and a lambda. So they would have to do a weak decay from that weak process that I mentioned at the beginning. In particular, a couple of them could be produced the same way, but decay to sigma C plus plus pi minus pi minus. So I'm predicting that looking at this decay, then one should be able to see peaks at around 3.8 and 4.2 GeV in sigma C plus plus pi minus pi minus. Well, Babar looked at that, and they noted in their paper that they did see peaks there. And so my first prediction for LHCb is that if you look at this same decay with more statistics, you'll be able to see peaks at 3.8 and 4.2 GeV that get to 5 sigma. So that's talking about isospin 1 and isospin 0 baryons with an F quark. There should also be isospin 1/2 baryons with an F quark that have an F and an S. And the lowest mass of these, if the quark has a mass of around 2.9 GeV, should have a mass of around 3950. The neutral version of this could decay to lambda C plus K minus. And so I'm showing all of the quark processes here, by the way. So Babar also looked at that, and they found an excess in the 3.8 to 4 GeV range and said a possible explanation was decay via a baryon resonance that has not yet been observed. So my second prediction for LHCb is that if you look at this decay, then you will also see an excess there. And if you have enough statistics, then you should be able to resolve it into two narrow resonances. The 3.95 is the one that I'm mentioning above there, and then the 3.8 was from the previous slide. So in this model, I'm saying that there is an additional quark. This F quark has a mass of 2.9 GeV in between the charm quark and the bottom quark. Well, if so, why are there no spikes associated with FF bar mesons in the inclusive hadronic cross section? There's spikes for CC bar, the lowest CC bar vector resonances, and the lowest BB bar vector resonances, but there's no spikes in between those in that cross section. And so why would that be? What's the explanation for that in this model? Well, why are there spikes in the first place? It's because the J psi doesn't have enough mass to decay to d bar. The upsilon 1s doesn't have enough mass to decay to b bar. And so what they can decay to, um, those decays are highly suppressed, and so they have long lifetimes and they're very narrow resonances. But in this model, the lowest vector meson state of FF bar, the analog of the J psi, can decay to the lowest F mesons in the model. And that's because the masses of those lowest F mesons are reduced, they're pulled down due to the scalar interaction, closer to masses of analogous CC bar mesons, which is the eta C. So one would not expect, if that's true, one would not expect to see narrow spikes in that range. In this range here, one would expect to see a wide resonance associated with the lowest vector meson of FF bar. So what does that look like? This is where the green circles are. That's where you would expect to see a wide resonance if the quark had a mass of 2.9 GeV. These data are from the 1980s. And so there isn't anything more recent there. Um, so I'm claiming that if there was more recent data in this range, it would reveal a 5 sigma resonance with initial state radiation corrections applied, with a mass of around 6,600 MeV and a width of around 200 MeV, associated with the lowest mass vector meson of FF bar. Okay, well, so could LHCb see this? Um, if this was created promptly in PP collisions, then it would decay far too quickly to be observed by LHCb. But the good news is LHCb can observe the decay products of upsilon 1s. And upsilon 1s could decay to FF bar mesons just as it decays to CC bar mesons. So these are the branching ratios for upsilon 1s decay to various CC bar mesons, including the J psi and the chi C1, chi C2. So the analogs of those in FF bar would be this resonance at 6,600 MeV with a width of around 200. And then the chi C1 and chi C2 should both be around 6,900 MeV, and they should be smaller widths. So they if they come from upsilon 1s, then it would be possible for LHCb to see them. The good news too is that due to the scalar, these FF bar mesons can decay to J psi, possibly also with a photon. And so in this model, that is my explanation for the J psi data that LHCb has seen. And it's also my explanation for why LHCb has been able to see these decays with these widths of resonances, and that they came from the upsilon 1s. So in this model, the lowest mass resonance is the 6600, which is a 1 minus minus, but it gives off a photon. And then the J psi part that is left over is mostly 2 plus plus. And then in the peak at 6900, that is mostly 2 plus plus, but it's also got some 1 plus plus and 0 plus plus in it. So then there's also a third resonance that CMS recently observed and is also seen in Psi2S data with Atlas. And it's also in this alternative model of LHCb. And in this, that is another resonance of FF bar that has 0 minus plus or 0 plus plus. So an interesting thing about this model, CMS recently did an analysis and found that a significant number of these decays must be 2 plus plus. And so that is well described in this model via what I mentioned up there. So those are FF bar mesons. The model also has mappings for FS bar mesons. So all of in this table, the left column are a number of observed exotic hadrons. Then it shows their observed width, their observed quantum numbers. All of those hadrons I am mapping to FS bar mesons in the quark model state that is in the fifth column. And that quark model state matches the quantum numbers in the previous column. Then in the last two columns, what I've done is I've said, okay, what what are the analogous meson states if I were to replace an F with an S or an F with a C? And what's the difference in the mass of those mesons compared to these exotic hadrons? And so those mass difference columns are very consistent. What that means is that the spectrum of these F mesons has a consistent mass spacing to spectrums of analogous SS bar or CS bar mesons. It also means that when you look at this, that they imply a mass of the F quark, again, around 2.9 GeV. I've also mapped a number of mesons to F, or a number of hadrons to FD bar mesons. And for all of these, the production and decay processes are explained by the light scalar and the W, and all of the observed quantum numbers um, are matched by the quark model mapping of these mesons. They're also consistent with a 2.9 GeV quark. This is where the 3872 lives, and since it's an FD bar meson, it means that it has charged isospin partners, and I'll talk about that in a minute. There's also the lowest mass meson here at 3250 is less than half of the mass of the FF bar at 6600, which is why it can decay into two of these. This one is listed in particle data group other mesons further states observed by a Russian collaboration in 1993. But what I want to look at is these two here. The 3350 was observed by Belle in 2006, and in that same paper, they saw 2.8 sigma evidence of the 3820. So this was the Belle observation of 3350, where it decays to lambda C plus P bar. And so this is described in the quark model process that I show there. They also saw evidence of a 3820 with a width of 30, or almost evidence, 2.8 sigma. And so my prediction for LHCb is that LHCb could confirm both the 3350 and also 3820 as resonances by looking at these same B meson decays with more statistics. So there were D F bar mesons I mentioned. So UF bar mesons are charged, and these are some charged exotic hadrons that I've mapped to those. In particular, you'll see that I've mapped the 3875 as the isospin partner of the 3872. And that is needs explanation because the 3872 is known to decay to CC bar, whereas the 3875 has been observed decaying to CC. So I'll explain later in this talk how the 3875 can decay to CC in this model. And but first, I want to talk about how the 3875 could also decay to CC bar, since in this model it is the partner of the 3872. In particular, the 3875 should be able to decay to K plus J psi. It's a very straightforward process with the scalar. The F bar goes to the S bar and CC bar. And so that should be allowed in this model. How could the 3875 be produced? It could be produced in E plus E minus collisions going to 4660, and then gluon would make that into a K minus and a T plus. So BESIII has looked at this, and these are their data there. And so my prediction for BESIII is that more statistics will generate evidence of a 3875 plus resonance of K plus J psi in that decay. There are other ways that a 3875 could be produced. It could be produced in a B plus goes to a T plus and phi. And so Babar looked at that, and this is what Babar saw. So in this model, I'm saying that that's a hint of the 3875 decaying to K plus J psi. So I have a prediction for Belle 2, which is that more statistics will reveal a 5 sigma resonance in this process. And that is only for B mesons coming from the upsilon 4s. Why is that? Because there can then be nothing coming from a BC decay that is included in the data. So I know LHCb has looked at this same process and sees no evidence of a 3875 resonance, has a lot more statistics. And what LHCb does see is a very big resonance of a T plus 4000. That was not seen in Babar data. So I'm claiming that that T plus 4000 is actually coming from a BC decay. And here's how that works out. The BC decays to a phi and the lowest vector meson of CF bar. Then that vector meson decays to K long K plus J psi. If the K long is unobserved, then it all has the right kinematics to look just like a B plus going to a phi and a T plus 4000, then the T plus decaying to K plus J psi. And that will, if so, that will wash out the 3875 signal. And for this to work, that vector meson, there's some range of masses it could be in. 4970 is my best guess for it. But it should have a very large branching ratio for this proposal to work. That's good news, though, because if it does have a large branching ratio, then LHCb should be able to see it in the same process, just replacing the K long with a K short. So looking at BC decays to phi, K short, K plus, J psi, I would expect a significant resonance for this CF bar meson. Another CF bar meson, the lightest one, I'm claiming could be seen in the decay BC go to phi and then lambda C plus lambda bar. And so in that, I think that LHCb should be able to see both the lightest meson of this and the lightest vector meson, the one I just mentioned on the last slide. If 3875 can decay to CC bar and CC bar can decay to PP bar, but 3875 has an S floating around from its scalar decay, then it should be able to decay to P lambda bar. And the quark processes for that are shown there. So in addition, the 3820, which is the charge partner of the one that I'm suggesting that LHCb should look for from the Belle evidence from 2006, that one should also decay to P lambda bar. So Belle looked at this process, and this is what they saw for that. And they noted an excess in the range of 3.5 to 4 GeV. In this model, that excess is because of those two decays, the 3875 and the 3820, decaying to P lambda bar. And so the prediction is that if LHCb were to look at this with more statistics, you would see an excess there as well, and hopefully with enough statistics, you could resolve it into two resonances. Okay, so if they are partners, 3872 and 3875, I've claimed 3875 can decay to CC bar. But it has been observed decaying to CC. And so for those to be partners, 3872 should also be able to decay to CC and to decay to D meson, D meson as well. How would that work? Well, the 3872 is an FD bar meson, and from the scalar, it can go to a pi zero and a zero plus plus configuration of CC bar. But what is a 0 plus plus configuration of CC bar with d mesons? To answer that question, it's best to rewrite the d mesons in terms of their C parity eigenstates, just as you would write kaons, neutral kaons, in terms of their C parity eigenstates. So 0 plus plus are made up of a D1, D1, or a D2, D2. Those are the only combinations that give 0 plus plus. So a 3872 should be able to decay to pi 0, D1, D1. And that's completely analogous to an F1 1285 decaying to pi 0, K short, which is observed. Also, the 3872 should be able to decay to pi 0, D2, D2. Well, could it decay to D, D bar? Well, if you assume that D1 and D2 are mostly the mass eigenstates and that they have slightly different masses, then from those two 0 plus plus combinations, you can't make a D, D bar state. And that's because the way you would make it is from D1, D1 minus D2, D2, but those two different terms have two different masses. So instead of doing that, you just say, well, the 3872 can decay to D1, D1, and it can decay to D2, D2. And when you add up all the diagrams, what you're left with is it decaying to D0, D0, or D0 bar, D0 bar. And so it's saying the 3872 can decay this way. It cannot decay in a three-body decay to pi 0, D0, D0 bar. So what am I saying? I'm saying that the 3872 has its dominant decay, which is to D0, D0 bar star, and then it has this much smaller branching ratio decay to D0, D0. But it has to be a lot smaller since it wasn't seen by your collaboration or by Belle. Um, Also, I'm claiming that 3872 cannot decay in a 3-body decay to pi 0, D0, D0 bar. And that agrees with the BESIII analysis that came to that conclusion. So if that's the case, and 3875 is the partner of 3872, well, it can't decay by the dominant decay because it doesn't have enough mass. But it can decay by the much smaller branching ratio decay, and that's what's observed. And so that's how I reconcile that aspect of those two being isospin partners. So I'm saying that the 3875 can decay to a pi plus and a 0 plus plus configuration of CC bar. Well, then that begs the question, could it just decay to pi plus and chi C0? And maybe it would be produced by a B meson decaying to a T plus and a K0. Well, LHCb has looked at that and looked at the branching ratio of that decay and found it to be quite large. It's particularly large when compared to the decay to a K star plus and chi C0, and also when compared to those same analogous decays going to chi C1. So that begs the question that in that decay, could there be a resonance in chi C0 pi plus? So I have a tentative prediction. I think this one is probably very easy to check, but I have a tentative prediction that in that decay, there should be a resonance or two narrow resonances of chi C0 pi plus, one at 3875, and there should also be another one, probably a bigger one, at 3985. But it's tentative because I have not worked out in detail the isospin selection rules and how they relate to this model as opposed to the standard model. Okay, I've been asked a number of times, okay, the theory has a light scalar. What is the mass of this light scalar? So I'm going to completely speculate here. I know the whole theory is speculation, but I'm going to speculate even further here. Um, so this is what I said was the main interaction of the scalar, connecting to CC bar and connecting the F quark with the S and the D. There are actually also smaller terms in that interaction. In particular, there's a connection of to SS bar with a smaller constant there. That means then that if the scalar is lighter than J psi and heavier than 1.5 MeV or 1.5 GeV, for example, it could go to it could radiatively decay from a J psi to a photon and this scalar. Then the scalar could decay to SS bar. So the real part of the scalar could decay to K short, K short. So BESIII looked at this and they saw, a couple of really nice peaks that are thought of as glue ball candidates. The F0 1710 has been thought of, for example, as glue ball candidate, but they've noted that there is some problem with that interpretation because glue balls should have similar decays to pions and kaons. But 1710 decays much more often to kaons, and that casts doubt on the glue ball interpretation. So a question is, part of the 1710, could it be the scalar? Um, then along those same lines, there's a pseudoscalar that has been observed, the 1835, that would have the right sort of production and decay to potentially play the role of the imaginary part of the scalar in this model. So that's just some speculation as to where the mass of that might be. Here are all the predictions I've said in this talk, the predictions for LHCb on one page. The left ones are ones where I've shown a figure and in a published paper, and I'm suggesting that LHCb should be able to, with more statistics, see observations of things that may be hinted within those figures. And so the size that I'm expecting for those resonances would be based on the hints in the figures. On the right side, I try to give some sort of percentage of how much of a decay would be provided by resonances. The first two are CF bar mesons, and then the last one is my tentative prediction of the 3875 and 3895. So summary is this is presenting a theory with the seventh flavor of quark. The mass is in between that of charm and bottom, charge minus 1/3. There's a light scalar that connects this quark to S and D and also to CC bar. The W boson connects this quark with the charm quark. If that is assumed, then the quark and the scalar together can explain the mass, spin, parity, production, and decay processes of most observed exotic hadrons. And so I've made a number of predictions based on that for where to find more exotic hadrons and how to see some new decays of already observed exotic hadrons. I'm claiming that a number of published papers have figures that could have hints of those predictions. And also, without proving it in this talk, I'm just stating that the underlying theory is free of anomalies and is able to reproduce experiments that would seemingly rule it out. There's a lot more about that in these archive links about the underlying theory and the details about fitting the observed exotic hadrons and the predictions. But these slides have my newest and most updated predictions, especially for LHCb. So that's it. Thank you. Are there questions?
Thank you, Scott. It was really nice talk. And thanks for all the predictions and to make this talk for us, especially. So we appreciate that.